This is a little problem-solving episode for Physical Science 103. And in lab number 5, States of Matter, the simulation from the PHET providers works okay for a while, but they're toward the end. Students have noticed that in steps number 14 and number 16, stability is kind of a wishful thinking. So I'm going to share the simulation so we can actually run the sim and see where the problems are and what type of response would be acceptable for a good grade. So you're going to have to pull out your hard copy of the method and have it ready, because I can't share both the hard copy and the sim. So I'm going to share the sim, and you have the hard copy in front of you. So when I reference number 14, you'll know where to go. All right, so we're going to share. And there's the sim. And you should be able to see the sim now. I'm going to expand it for my purposes. And there we go. Now, by this time in the method, you will have arrived at the point where the instructions say, click on phase changes down here. So you go into the phase changes. And what it may do, excuse me, what the sim may do is just remember where you were at the last time, which would have been neon. But number 14, and I believe that's on page 3 of 4, number 14, it says use oxygen. So we'll click on oxygen and get that one ready. And there's always a primary objective with any type of lab exercise that I require my students to do. And in this case, we're not just looking for numbers. We're looking for your ability to recognize what a solid looks like, what a liquid looks like, and what a gas looks like in the simulation. Right now, what we have is oxygen as a solid. And you'll notice the regular arrangement of the molecules. If it were a liquid, then it would still be clumped in a definite volume, a definite space, but the molecules would be random. And of course, if it were a gas, then all of those molecules would be spread out completely in the container, be separated. So those are the 3 phases we're interested in. And at this point, it's a solid. And you'll notice that the method calls for record the initial pressure. All right, so you look up here, and of course the pressure is 0. And that stands to reason, because in order for pressure to be measured, you've got to have contact with the element and the pressure measuring device. And the pressure measuring device is way up here, and the oxygen's way down here. So it's sensing nothing. In other words, in order to get a pressure out of it, you're going to have a gas. Okay, so you would expect the initial pressure to be 0 atmospheres. Then it says to take this finger and click and hold, and then move the finger down. Okay, so what are we doing? We're reducing the volume of the container. And at this point, oxygen doesn't care, because it's not occupying any of that volume. It's all solid. So we'll come down until the the plate that we're pushing on touches on the oxygen, and you should see it if we very carefully lower this plate onto the oxygen, it's going to distort it. Now, it's very easy to go past this point. We're touching it now, but it's still a solid. So let's go a little bit closer. Okay. Just, okay. Now you notice the temperature jumped up. And so did the pressure. Right? Uh-oh, we went too far. Now we're making a liquid. Okay. So at this point, I have to start over again. So we'll click the reset button and be sure we've got oxygen again. Okay. Now I'm going to go down. And the pressure is being measured because we're seeing a pressure because the plate and the sensor that's attached to the plate is actually touching. So if I let my click loose so I can move this around, notice that the pressure is up 0.2, 0.3, it varies. It's moving around. So at what point is it going to stabilize? The idea here is to stabilize it at just where it starts to turn liquid. Okay, that's pretty close. So we're reading around 6 atmospheres. And notice also that with this increased pressure, reduced volume, and the plates actually touching on there, we're increasing the pressure. We've still got some solid here, but occasionally you're going to see some of these molecules rearrange. So we're right on the border between changing it into a liquid and keeping it a solid. Now this value, the pressure and the temperature, of course, the method doesn't ask you for that yet. Doesn't ask you for the temperature. That's in step 16. But at this point, we're noticing a pressure that's jumping around somewhere around 6 atmospheres, and it's not very stable. So that term that's used in the method where it says record the pressure that stabilizes after reducing the volume. Okay. It can be almost anything. Like I said before, the objective here is for you to recognize what does a solid look like, what does a liquid look like, and what does a gas look like. And there needs to be some type of pressure, right? Otherwise, you have to put 0 in there, and that would defeat the purpose. For the item in the method that calls for reduced volume pressure. And besides, the method says push that finger down until the oxygen becomes distorted, and that's what it's doing right now. So you would record in your reduced volume pressure. In this case, it looks like it's stabilizing around 5 now. So, you know, it's a wide range, and I take that into account when I'm grading. Okay, so number 14, that one's done. Step 15 says click the reset button. Okay, so we're going to do that. And then we're going to go down to 16. Let's see, there's 16 on the same page. And we're using oxygen again, so we got to be sure that we've got oxygen in there. And notice something about the oxygen. Let's look at neon again, right? Individual atoms of neon. That's typical of noble gases. They don't form molecules with other neons. They're independent atoms. Whereas oxygen is going to be diatomic, right? So we're going to have, it's going to be like that, actually, if you draw out the formula. but the way it's represented here, it's right. It's two oxygen atoms like that. You don't have to know that to answer the questions. I just thought I'd mention it. Okay, so oxygen's still a solid. We've got 0 atmospheres and the temperature is 27 K. Right? Everybody knows what K is. K is Kelvin. Right? And if I don't know if I think that you've been introduced to Kelvin, but Kelvin temperature is equal to Celsius temperature plus 273. Right? So if you had let's see. No, the other way around. I'm sorry. No, that's right. That's right. If we subtract 273 from 27, then we get a negative number, right? So negative degrees Celsius. And that's not absolutely necessary either. Okay, what does the method say? Heat up the container. So that's down here. Right? So we would move this thing up and show a few little flames. And I like to do it little at a time, right? Just little so you can watch what's happening, right? And we've heated it up to 36 K. And notice that the molecules are becoming more agitated. We're adding energy to the oxygen mass. And it's still relatively solid in form. In other words, the molecules are regularly spaced. So I think we've still got a solid. So let's heat it up just a little bit more. All right, so you see the temperature's going up 40 K. And the method says, heat up the container and record the stabilizing temperature and pressure without changing the container size. All right, so we're not going to change the volume, but we want a stabilizing temperature. All right, so where is the temperature stable for solid versus liquid? That's what we're looking for. So we're going to have solid in the left-hand column of our, in the document that you're filling out, and then liquid in the right-hand column. Okay. And then when we apply heat, okay, what is it doing? It looks like it's still solid. Notice how regular the arrangement of the molecules. Okay, so we need to heat it up just a little bit more. They're getting pretty agitated. It's still solid. So if you click and hold this slider, and then when you release it, when you unclick it, it'll drop back down to 0. It's kind of like the steering wheel on your car, right? You're turning the curve. All you have to do is let go of the steering wheel, and it self-centers. So this slider is the same way. So we'll heat it a little bit and then let go. And then heat a little more and then let go. It's getting more and more agitated, but you still see some regular arrangement of the molecules. That says it's still a solid. Now, it may be changing shape as a solid, but it's still reasonably solid. What we're looking for is when the arrangement of the atoms is, the molecules are random, and they're getting pretty close. So 53 K might be a valid number. Let's heat it a little more. Some of them are still regular arrangement. What we're looking for is the transition temperature from solid to liquid. We're almost there, actually. And you can tell when you've made the transition, if you focus on maybe 2 or 3 molecules and say, all right, those guys are regularly arranged. Oh, no, they move. They changed position. If that happens, then you're pretty close to the transition state. I think we're pretty close. So let's keep that in mind, 60K. And another indicator is the pressure, right? As long as the pressure is 0, then the gauge is not measuring any impacts from the molecules. Some of them are still regular, but a lot of them are not. So it's kind of a guessing game. I think we're pretty close. And another indicator also is, has the volume changed? That mass, right? And the way okay, there you go. See, one of those molecules is broken loose, right? So it's starting to put molecules into the gaseous phase. And I think we're out of liquid now. We could cool it down a little bit like that. Cool it down just a little bit more. So right in that range would be an acceptable temperature, say 62 to 63 K, and with 0 atmospheric pressure. I mean, 0 atmospheres pressure. Okay, so let's see. Pressure without changing the container size. Okay. Let's keep heating it up. All right, we've definitely got a liquid there. Okay, we're up to 70 degrees. Let's heat it some more. So the gauge is actually measuring some pressure now because we've got molecules in the gas phase. So for the liquid side, you could pick any one of these temperatures, 94. Let's make it all gas. Okay, pretty close. So you recognize that a gas is going to have all of those molecules separate from one another. Still got some of them a little too close down here. Okay. So we're in a usable range now. There we go. 137 at 5 atmospheres. Oh, we gotta wait. It's really bouncing around in it. I can see the problems that you're having judging stabilization. Right. So it's not perfect. So then the second step in number 16 is cool it down until you find a stabilizing temperature and pressure. Right, so we've got complete gas here. Let's cool it down some. Give it a chance for the simulation to stabilize. All right, we still got a gas, but some of them are starting to collect down here and over here. Let's cool it just a little bit more. And watch it for a second. Are we starting to get any liquid forming? Some right in here, maybe a few over here. They're starting to associate with one another. So think about what's happening here on the molecular level. Molecules do interact with one another. And in this case, they're all the same molecule. They're oxygen molecules. So when they encounter one another, there's a certain amount of attraction. And that varies, right? Depending on the molecule, how much attraction is there between each molecule. If you add energy to a collection of those molecules, then they vibrate too fast, they move too fast, and they overcome those attractive forces. And that's what makes a solid turn into a liquid and a liquid turn into a gas. We put enough energy in there to overcome those attractive forces. If we pull energy out of the group of molecules, then those very weak forces will cause the molecules to attract one another. And that's how you get condensation from a liquid to a gas to a liquid and a liquid to a solid. So we see some interaction here, and this is in the neighborhood of stabilization. I'd say 121 K at 2 atmospheres. Okay, so that would be for the liquid side. So let's cool it down some more and see, before we went up from the hots, we heated it up, and now let's cool it down and see if we get a similar response. So now we're going to go to the point where we've just barely got maybe one gas molecule bouncing around and everybody else is a liquid. So let's cool it down. See, the motion is starting to decrease and we're seeing more and more interaction between the molecules. Give it a chance for the simulation to stabilize, in quotes. Looks like we've got some liquid down there forming, but there's still a little too much gas. Let's cool it a little bit more. More. Okay. We don't want to cool it too far, we'll make a solid. We want to get right at the point where it stabilizes. Okay, it's getting there. See, they're starting to clump together. Cool it some more. Okay. Well, now that looks like a liquid to me. But are we starting to form any solid yet? That's the question. Okay. Now there's some regular arrangement showing. Let's try to get some of those gas molecules back in the group. Got one more. See, he's bouncing around over here. Come on. Let's be patient. Maybe there'll be some attraction there. I think we got it. Okay, so now we're just on the edge of solid liquid. And that's at 55 K and 0 atmospheres. Okay, so it'll vary whether you're heating up or cooling it down. And I'm pretty liberal with that. Oh, there was in the method number 16, I see that it's solid, liquid, and then we have some information here for heat and cold. Okay, so the heat, these values in heat were when we were heating it up, and then this side was when we were heating it up even more. Okay, so we got those values that we should have recorded in there as we obtained them. And then we cooled it back down. And when we cooled it, we were looking for actually, we need to cool it even more. Because that arrangement is not quite regular enough. Remember how it looked when we first started the simulation? It's not there yet. Okay. Now we've fixed everything in regular arrangement. It looks like they're not moving anymore. So when we're cooling it down, we're looking for where the solid occurs, right? And in this case, it was 24 K and 0 atmosphere. Okay, so I hope that helps. Let me see, is there anything beyond that? Okay, the last section, I don't know if you'll have trouble with this one or not, but I'll talk about it anyway. Number 17. So we're going to click on reset. Right. It automatically goes back to neon. And then number 17 says choose any type of atom or molecule, neon, argon, oxygen, or water. Doesn't matter. So we've done oxygen, we're doing it. Let's do argon, just for argument's sake. And create an experiment using this simulation. Describe the experiment below by altering the number of particles using the pump. Right. All right, so we can put, I'm just holding the click button down and moving this pump up and down. Describe the experiment below by altering the number of particles, the temperature by heating and cooling, or volume. So you can do any one of those three. Either change the pump, add more particles, change the temperature, or change the volume. And then say, what conclusion can you derive from that? Well, the experiment description is you make up your own, right? What are you going to do, right? Am I going to change the temperature? Am I going to change the volume, right? Or am I going to change the number of atoms? And say, what happens? So in the document, we've got a description, right? So that's where you describe your experiment. You say, what atom did I use? Which variable did I change? Did I change the pressure by moving the finger? Did I change the temperature? Did I change the number of molecules or atoms? Okay, and then what do you expect to happen? Anytime you create an experiment, you are supposed to speculate on what the outcome might be. If you don't do that, then you're not testing anything, right? You're just shotgunning. You're just saying, let's go in the lab and play. But if you're conducting an experiment, you have an objective in mind. You want to test a question that you have. Sometimes we call it a hypothesis. So you say, what do I expect when I increase the temperature from such and such? Let's go back. Let's reset it and go back to argon. So the temperature you're starting with is 43 K, right? So what happens if I say, I'm going to start at 43 K and I'm going to increase the temperature, right? What do I expect to see? And it can be in general terms, right? Well, I expect eventually to see the formation of a liquid. And then if I heat it more, a formation of a gas. So in the section below, now you describe your experiment, and then you have the type of molecule, in our case, argon, and then you have final temperature, right? So if you change the temperature, what is that temperature going to be? If you don't change the temperature, that's fine. But there's also the possibility for a final pressure, right, in atmospheres. So if you change the pressure, then you record that. But if you didn't record if you didn't change the pressure, then that's fine. If you did change the number of atoms in there by working the pump, then the final temperature and the final pressure will change. And then you draw conclusions. So let's say we actually change the pressure. So how do we know what we've done with the pressure? Well, let's reset, go back to argon, and we're not going to touch anything but the number of altering the number of particles. Right? So how many particles do I have in there? Yeah, we'd have to count them. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Looks like on average 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 8, 64. So you start off with 64 particles, 64 atoms. And then we're going to add to them. Notice the pressure is 0. Right, we just added 4. Added 4 more, so we're up to 8. We've added 8. 3, 11, 12, 13, 14, 15, 16, 17. So we added 17. So what happened? Well, what was the initial temperature? We didn't record it, right? So final temperature is 95 K. I think the temperature was lower than that. Plus, pressure didn't register anything. So we added that, and we didn't change the temperature. We didn't change the temperature. The temperature changed on its own, and the pressure changed on its own. So what are your conclusions, right? Well, you might say something like, I started off with 64, I added 17 atoms, and the temperature changed from this to this. Well, when you designed your experiment, did you speculate? When I add these atoms, what's going to happen? Is the temperature going to go up? Is the pressure going to go up? Right? So you say in your proposal, in your description, your proposal, you say, I expect the temperature to go up. I expect the pressure to go up. You may not know how much, but you have those expectations. And then did the results of the experiment satisfy those conditions? So that's the idea. Try to get you thinking in terms of experimental design, testing by doing the experiment, and then conclusions. What were the results? Did they agree with what you thought they would be? And they don't have to, right? They can be different than you expected. That's all right. Negative results on experiments are not bad results, right? The best that negative results can do is point you in a different direction. So I wouldn't worry about the results being different than your proposal. just that you record those in the document and say, what did you do? What are the results? Did they agree with what you expected? And that's it. And that's why this part of the exercise carries 10 points, because it requires you to think. And thinking is more important than rote memory or cookbooking. All right, up to this point, we've done pretty much cookbooking. This one, number 17, is where you have to think. And by design, there's room for doing what you want, right? That's the beauty of experimenting. When you design an experiment, you can design it any way you want. But when you finish, you've got to be able to say something about it, right? Was I right? Was I wrong? And then in reality, if you do this for a living, if you do research for a living, then you're going to have to publish your work, and everybody who reads your publication is going to expect you to say, all right, where do we go from here, right? What are the results? Tell me to do next. All right, so I hope that helps, and good luck.